Good morning to all of us. Today's topic, we're going to discuss what is permeability. So, permeability is the measure of the soil's ability to permit water to flow through its pores or voids. Any material with void is porous, and if the void are interconnected, it possesses permeability. So, therefore, rock, concrete, soil, and many engineering materials are both porous and permeable. However, among them, soils, even in their densest state, are more permeable. So, sa lahat ng nabanggit nating example kanina is yung soil yung pinaka-permeable sa kanila. So, yung permeability is ito yung ability ng tubig na dadaan, passes through yung mga materials natin. So, we have a figure here. So, example ito ng soil. So, we have a loose soil and a dense soil. So, in this figure, sa kabila is, as we observe, yung mga grains dito is hindi sila compacted or hiwa-hiwalay sila. So, the water will easily flow through it and then it will have a high permeability kasi madaling dadaan yung tubig. So, in the other side naman is we have a dense soil dito. Yung mga grains natin is they are compacted or dikit-dikit sila. So, yung tubig natin is it will difficult to flow. So, it will lead to low permeability. So, next is we have the importance of permeability. Ito yung mga kaimportantehan ng permeability natin. So, first is permeability influence the rate of settlement of a saturated soil under the load. The stability of slope and retaining structure can be greatly affected by the permeability involved. So yung mga structures natin, yung mga ginagawa nating structures is they are being affected sa permeability ng materials na magagamit. So the soil of earth dams is very much based upon the permeability of the soil that being used. So as I said earlier, yung mga design ng dams natin is nakabase siya sa permeability ng soil na magagamit. So next is the filter made of soil are designed based upon their permeability. Next is we have the Bernoulli's equation. So from fluid mechanics, we know that according to Bernoulli's equation, the total head at a point in water under motion can be given by sum of the pressure, velocity, and elevation head, or total head is equals to pressure all over the pressure head plus velocity squared all over 2 multiplied by g. Yung g natin dito is ito yung tinatawag natin na acceleration due to gravity plus z. Ito yung elevation head natin. So next is we have the elevation head z is the vertical distance of a given point above or below a datum plane. Pressure head is the water pressure U at the point divided by the unit weight of water. So, dito natin na-derive yung mga formulas. So, at any point, H is equals to Z plus U all over YW. So, sa head loss between A and B naman is we have delta H is equals to HA minus HB. Or pwede rin siyang makuha through ZA plus U sub A all over YW minus Z sub B plus U sub B all over Y sub W. Kapag head loss between A and B yun. Pero kapag head loss in non-dimensional form naman is yung gagamitin natin is yung I is equals to delta H all over L. Where yung I natin is yung hydraulic gradient, yung H natin is difference in total head. L naman is distance between point A and point B. So paano natin na-derive yung I is equals to delta H all over L. So dito siya. So sa hydraulic gradient naman is in the field, the gradient of the head is the head coefficient over the distance separating the two wells. So in finding I, we will use this formula. I is equals to H1 minus H2 all over the delta X. So, hydraulic gradient, dito makukuha natin yung sinabi ko kanina. So, we have I, it is equals to H sub A minus H sub B all over L. Or pwede natin siyang i-derive as I, it is equals to delta H all over L. So, next is we have here the Darcy law. Wait. In general, the variation of the velocity V with the hydraulic gradient I, as shown in figure 7.2 dito siya. So, ito yung figure natin. So, laminar flow zone, ito yung zone 1. So, from here to this point. Transition zone, ito yung zone 2 natin, dito siya. Turbulent flow zone is dito naman. So, yung pataas na line is ito yung velocity natin, which is the V. And yung dito naman is the hydraulic gradient, ito yung I natin. So, in most soil, the flow of water through the void space can be considered laminar. Thus, discharge velocity multiplied by hydraulic gradient natin. So, in fracture rocks naman, stones, gravel, and very coarse sand, turbulent flow condition may exist and V multiplied by I may not be valid. So, dito naman is there is a condition which is yung turbulent flow condition may exist pero hindi siya valid. Next is we have the Darcy law. Darcy law. In 1856, Darcy published a simple equation for the discharge velocity of water through saturated soil which may be expressed as V all over Ki. Where yung V natin is ito yung discharge velocity, which is the quantity of water flow in unit time. Through a unit cross, multiplied natin siya sa 0,002. Sectional area of soil at right angles to the direction of the flow. Yung K natin, ito naman yung hydraulic conductivity natin. Otherwise, known as coefficient of permeability. Yung I natin, hydraulic gradient, it is equals to H all over L. Then the quantity of water flowing through the soil per unit time is discharge, it is equals to Q. It is equals to V multiplied by A. It is equals to K multiplied by H all over L multiplied by the A. So, ito yung flow in soil natin, which is, ito yung on how we derive with the formulas dito sa baba. So, I, it is equals to HA minus HB all over L. As I said earlier, we can write this as delta H all over L. So, in finding Q, it is equals to KIA. So, yung I natin is pwede natin siyang palitan. So, K delta H all over L multiplied by A na siya. Next is to determine the quantity of flow, two parameters are needed. So, we have the K and I. Yung K natin is yung hydraulic conductivity. Ito yung how permeable the soil medium is. Yung I naman natin is ito yung hydraulic gradient. How large is the driving head natin? So, yung K natin is pwede natin siyang ma-determine into 3 testing. So, first is we have laboratory testing. Sa laboratory testing, yung ginagamit natin is yung constant head test and yung falling head test. Sa field testing naman, we have the pumping from wells. And then yung third is yung empirical equation yung ginagamit. Sa I naman is pwede siyang ma-determine through from the head loss and geometry. Yung number 2 naman is yung flow net. So, yung remaining slides will be discussed by my group mates. So, yun lang. Thank you.
So, let's move on to hydraulic conductivity. What is hydraulic conductivity? The hydraulic conductivity is a measure of how easy the water can flow through the soil. The hydraulic conductivity is expressed in the unit of velocity. It can be centimeter per second and meter per second. Hydraulic conductivity of soil depends on several factors. First here is the fluid viscosity. As the viscosity increases, the hydraulic conductivity decreases. The hydraulic conductivity for given soil becomes lower when the fluid is more viscous than water. Next is the pore size distribution. Sandy soil has a larger pore that absorb water faster, and it holds water per unit of depth. Dito, pag mas malaki ang pores ng soil, mas madali siyang mag-absorb ng water like sandy type soil. Next is the temperature. Hydraulic conductivity increases with increasing temperature. Next is the grain size distribution. The larger the average grain size of a medium, the greater the hydraulic conductivity. Last is the degree of soil saturation. Saturated hydraulic conductivity is affected by both soil and fluids. It depends on the soil porosity as well as the fluid's viscosity and density. The hydraulic conductivity for a given soil becomes lower when the fluid is more viscous than water. It is conventional to express the value of K at a temperature of 20 degrees Celsius. So we have a formula here. K sub 20 degrees Celsius is equals to viscosity at room temperature C, all over viscosity at 20 degrees Celsius multiplied by K sub room temperature of the sea. So we have a table here. Typical values of hydraulic conductivity of saturated soil. For the soil type, for the clean gravel, it has 100 to 1.0 K all over centimeter per second, and it has 200 to 2.0 K all over feet per minute. Next is the coarse sand. It has K centimeter over second. For K all over centimeter per second, it has 1.0 to 0.01. And for K all over feet per minute, it has 2.0 to 0.02. Next is the fine sand. For fine sand, it has 0.01 K all over centimeter per second, and it has 0.02 to 0.002 K feet per minute. So let's move on to silt clay. For silt clay, it has 0.001 to 0.0001 K all over centimeter per second, and it has 0.002 to 0.0002 K feet per minute. For the clay, it has less than 0.000001 K all over centimeter per second and less than 0.000002 K all over feet per minute. Next here, we have the laboratory testing of hydraulic conductivity. There are two standard laboratory tests to use to determine the hydraulic conductivity of the soil. First is we have the constant head test, and the second is the falling head test. So let's proceed to constant head test. Constant head test is used primarily for coarse-grained soil. This test is based on the assumption of laminar flow based on the Darcy's law apply. From Darcy's law, we have an equation here. Q is equals to K multiplied by I multiplied by A and multiplied by T is equals to K multiplied by H all over L multiplied by A and multiplied by T, where Q is the volume of the water collection and A cross-section area of soil specimen, and T is the duration of water collection. So we have a derived formula here. K is equals to V multiplied by L all over H multiplied by A and multiplied by T. Then let's compute this one. K sub 20 degrees is equals to viscosity at room temperature C multiplied by viscosity room temperature at C all over N at 20 degrees Celsius. This picture is an example of the constant head test. So we have a picture and a figure here. You can see tubes and some materials here to use in the constant head test. So let's move on to falling head test. When we say falling head test, it is mainly for fine-grained soils. We have a figure here. This is the simplified procedure. First, record initial head difference. H1 at T1 is equals to 0. Next, allow water to flow through the soil specimen. And next is record the final head difference H2 at time T is equals to T2. So we have the calculations here. K is equals to A all over AT multiplied by 1L multiplied by H1 all over H2, where A is equals to cross-sectional area of a soil. Small a is the cross-sectional area for a standpipe. H1 is the distance to the bottom of the beaker from the test. And H2 is the distance to bottom of the beaker after, this is after the test. H1 is before, H2 is after the test. L is the length of the sample. This equals to T1, T2 minus T1. Then let's compute this one. K sub 20 degrees Celsius is equals to K T degrees Celsius multiplied by viscosity at room temperature C all over viscosity at 20 degrees Celsius. So we have this one. K is equals to AL all over AT multiplied by 1 and multiplied by H1 all over H2. The above equation is the derived assuming the flow through the standpipe is equals to the flow through the soil. Derivation of falling head equation. The rate of the flow of the water to the specimen at any time plus can given by Q is equals to K multiplied H all over L multiplied by A is equals to negative A multiplied by DH all over dt. This will be our equation 7.20, where Q is our flow rate and A is a cross-sectional area of the standpipe. A is a cross-sectional area of the soil specimen. Let's rearrange this one. dt is equals to AL all over AK multiplied by negative DH all over H. That will be our equation 7.21.
Okay, let's go over for the continuation of the derivation of the falling head test. So for the integration of the left of the equation 7.21 with the limits of time from that is to time and the right side with the limits of head difference from h sub 1 to h sub 2 that gives that t is equal to a multiplied by length all over a multiplied by k, wherein the k is the hydraulic conductivity, and multiplied in logarithmic e h sub 1 all over h sub 2. So that is the equation. So let's go for the next slide. Next slide. So we have here the limitations of laboratory tests for the hydraulic conductivity. So first, it is generally hard to duplicate in situ soil conditions such as the stratification. So the second one wherein the structures of the situ soils may be disturbed because of and sampling test preparation. For the third one, the small size of the laboratory samples lead to effects of boundary condition. So these three are the limitation of the laboratory test for the hydraulic conductivity. So let's go over for the next slide. So we have here the determination of hydraulic conductivity in the field. So first is the pumping wells with observation holes. Second is the bare hole test. And the third one is the Packer test. So let's go over the next slide. So we have here the permeability test using the pumping wells. So this is used to determine the hydraulic conductivity of soil in the field. So when we say hydraulic conductivity, this is to measure on how easily water can pass through soil or rock. So during the test, water is pumped out at a constant rate from a test well that has a perforated casing. So several observation walls of various radial distances are made around the test. So continuous observation of the water level in the test well in the observation wells are made after the start of the pumping unit as it was steady state is reached. So the steady state is established when the water level in the test our observation wells becomes constant. So that is the test using pumping wells. So next slide. So on this part, we have here the pumping well with observation holes. So for the aquifer soil or the aquifer is a soil or rock forming stratum, I should say, that is saturated and permeable enough to yield. So on this part that is saturated in soil or rock for the aquifer. So for the confined aquifer, this is an aquifer confined between two impervious layers. So example for that is the clay. For the aquifer is the example for that is the sands, gravels, and the fractured rock. So we have here the figure. So we can see on the figure that on this on the part of the unconfined aquifer, nakikita dito sa taas. So dito sa figure, yung unconfined aquifer natin is nasa taas. So mostly na nandyan is either sands, gravels, or the fractured rock. So nakikita rin naman dito sa figure may naka-stated na sand. So yung nandyan is sand. Sa baba naman, dyan is yung mga confined aquifer. So mostly na nandyan is clay. So meron din sand na nailalahok. So on this part is sa confined aquifer is nandyan yung dyan nakalagay yung mga clay. So that is the difference between unconfined aquifer and confined aquifer. So let's go over to the next slide. And so we have here the pumping well with observation holes. So for the pumping well in an unconfined aquifer is, we can see on the figure based on the legend stated below. So for the impermeable layer is yan yung blue na may dots. So yung impermeable layer natin is nasa baba. So based on the legend is yung baba ang impermeable layer natin. So for the test well is the gray one, which is colored in gray. So nasa taas. That is our test well. So for the observation wells is yung may pa-zigzag sa figure. So may mga stated na part sa taas where is we can define the R or we can locate the R. So we have here the equation for the formula or the equation of decay, which is K is the hydraulic conductivity. So K is equal to 2.303, which is this is the constant the constant given constant to na given. So 2.303 multiplied by Q, which is Q is the flow rate, multiplied by logarithmic 10, R sub 2 all over R sub 1. This is divided into pi all over H sub 2 raised to 2 minus H sub 1 raised to 2. Or it will be simplified as K is equal to Q ln R sub 2 all over R sub 1. This will divided into pi multiplied by H sub 2 raised to 2 minus H sub 1 raised to 2. Then if Q, we have to take note of here that if Q and the H sub 1, H sub 2, R sub 1, R sub 2 are known, then K can be calculated. So that's it. Let's go for the next slide. We have here the pumping well with observation holes. So for the pumping well observation holes, we can see on the figure and with the basis of the given legend, for the impermeable layer, that is the dark blue, which is may mga dots. Ito yung mga colored in blue na may dots. So on that part, in this figure is the impermeable layer. So for the confined aquifer, that is the light blue na may dots. And for the test well is that is the gray one dito sa may gitna. And for the observation wells is yung pazigzag. Dito yung parang may pakat na on the right side. So that is the impermeable layer, confined aquifer for the test well and observations well. So the equation we are going to use is K is equal to Q multiplied by logarithmic 10 R sub 2 all over R sub 1 divided into 2.727 multiplied by H times H sub 2 minus H sub 1. Then if Q and the H sub 1, H sub 2, R sub 1 and R sub 2 are known, then K can be calculated. So that's it for the confined aquifer. So for the example, we have here a given example. So first example is, we have here refer to the constant head permeability test arrangement shown in the figure 7.5. A test gives these values. L is equal to 30 centimeter and A is equal to 177 centimeters squared, which is the area of the specimen, and H is equal to 50 centimeter, which is the constant head differences. And for the time, on the time in the period of water collected in time of 5 minutes, we have here 350 centimeter cube. So the given is Q is equal to 350 centimeter cube, and for the length is equal to 30 centimeter, and for the area is equal to 177 centimeter squared, and for the H is equal to 50 centimeter, and time is equal to 5 minutes. So we have here, so yung gagamitin natin na formula for to calculate the hydraulic conductivity So yung wag nating kakalimutan yung ating unit, that is centimeter per second. So K is equal to Q multiplied by length all over A times H times time. So yan yung ating formula. So let's simplify the given problems. So K is equal to 350, that is the Q, multiplied by 30, that is the length, all over 177, that is the area, multiplied by our H, which is 50 centimeter, times 5, which is the time, and for the second, that is the 60. So for that, we can compute now the equation. So yung answer natin dito is, yung calculated natin is 3.95 times 10 cube centimeter per second. So that is the calculated hydraulic conductivity in centimeter per second. So let's go over for the second problem. So we have here the second problem. For a falling head permeability test, the following values are given. Length of specimen is equal to 8 inches. Area of soil specimen is equal to 1.6 inches squared. And area of standpipe is equal to 0.06 inches squared. And for the head difference of time is equal to 0 in 20 inches. And for the head difference at time t is equal to 180 seconds in 12 inches. So same with the problem number 1, we have to determine, or the required here is the hydraulic conductivity of soil. So sa first problem, yung unit natin is centimeter per second. So yung unit din naman natin dito na hinahanap ng value ng hydraulic conductivity is inches per second. So we have here the given. For the area is equal to we have here the area is equal to 0.06 inches squared, and for the length is equal to 8 inches, and for the A is equal to 1.6 inches squared. For the time is equal to 180 seconds. For our H1, this is equal to 20 inches. So as it was stated, the time is 0. For the H2 is 300 mm. So the equation we are going to use, or the formula, is K is equal to 2.303 times AL all over 80 logarithmic 10 multiplied by H1 all over H2. So let's simplify the formula. So 2.303, that is the constant given. So yung A natin, which is the area of the standpipe, that is 0.06 multiplied by 8, that is the length, all over 1.6, which is the area, 1.6 multiplied by 180, the time in second. Tapos ilalagay din natin yung logarithmic, which is the logarithmic of 10, and multiplied by 20 all over 12. Yung 20 is the H sub 1, and for yung 12 is yan yung H sub 2. So in computing this, we will get the 8.52 times 10 raised to negative 4 inches per second. So ito na yung ating hydraulic conductivity. Ito na yung hinahanap in this problem, which is 8.52 times 10 raised to negative 4 inches per second. So that's it. So next slide. Okay, so that's the end of the lecture about the permeability. Thank you for listening.